quite complex title to my talk, which a simpler way of putting this is taking a low power display and making it even low power. And what I'm going to be talking about today is passive matrix addressing of LCD. So it's really only a topic familiar to the older members of the audience. But before that, because we haven't talked about ZBD SID for around about 10 years, I'll go back and say what this display technology is. So let's start with introduction. This technology was first invented in the mid-90s at a government lab in Malvern in the UK. And our first publication SID was actually 25 years ago this year. And a bit later in 2000, we spun out into a startup, did the technology transfer and mass produced many millions of products for shelf labels. So this has been very successful in the shelf label market. And then more recently, the team and the technology was acquired by New Vision Display. And now we manufacture it on a passive matrix production line at our Yongzhou campus in Hunan province. And we now market and sell this for all sorts of applications. So here's a couple of mass production products, 1.1 inch, 12.4 inch, and we make much bigger sizes as well. What is the ZBD configuration? We take a normal passive matrix LCD, pneumatic LCD, and on one surface we have a standard rub poly. On the other surface we put a sub-micron diffraction grating, and that diffraction grating stabilizes two surface pre-tilts, and they then stabilize two bulk configurations which can provide black and white pixels with appropriate polarizer configuration. We've shown a hand to TN example here, but it could be a hand to VAN or VAN to ECB. So you can use this bistable pre-tilt in a variety of optical configurations. So really we're adding image memory to a passive matrix LCD. It's worth going into a little bit more detail on this ZBD surface because there's a lot of science in here. When we take a grating surface with a perpendicular boundary condition, that imposes bend and display energy on the neighboring liquid crystal. And it's possible to relax some of that energy by creating a pair of singularities or defects on the peak and the troughs of those grooves. So this configuration here has a little bit of bend and display, but it has the energy of these two defects. And we can adjust the energy of these two states with respect to each other by just adjusting the D over P ratio of that grating surface. The homeotropic anchoring is important for another reason, because it provides minimal molecular interaction. We saw a talk earlier about zero anchoring on a planar surface, and it's very hard to avoid image sticking in that case. For homeotropic anchoring, you sort of get that fundamental with the surface. We also use this distortion. When you distort a pneumatic liquid crystal, you take a microscopic property called flexoelectricity and create a macroscopic flexoelectric polarization from that. And luckily for us, the net vector in one state points out of the surface and the other state points into the surface. So it gives us a polarity-dependent dressing method to move between the states. And as I showed in the previous slide, when we look a little bit above the surface, we see two pre-tilts, typically 90 degrees and around about 5 degrees for those two states. So we have a simple polarity-dependent way of selecting between the two states. We can use a monopolar positive pulse, which takes us from the C state continuous to the D state, which has these little defects in it, and then negative pulse takes us the other way. We prefer to use bipolar pulses rather than a monopolar pulse. In this case, it latches on the second half of the bipolar pulse, and this allows us to get good DC balancing, which is useful in a display. Also, you'll note here that I've made this amplitude smaller in the bipolar than the monopolar case, and that's what we find in practice, because we get a little bit of pre-poling from this opposite pulse. And this difference between monopolar and bipolar pulses is important for float addressing, which I'll come on to. But also, these defects, you create or annihilate these defects in pairs. There's quite a well-defined threshold for getting backwards and forwards. If the voltage is insufficient, nothing happens. other than an optical transient. And that threshold bistability is very, very important for backplane simplicity. So if you have ZBD, which is bistable LCD mode with a threshold, then your backplane is simply row and column electrodes, so there is no active matrix on there. You can go to the other extreme where there's no bistability in the LC layer, and you have to do all the bistability now in the backplane. So this is a memory and pixel display, which is a DC-powered ring oscillator behind every single pixel. And then there's a sort of intermediate type technological step where you have e-ink EPD, where you have a display medium which is bistable, but there's not a sufficient threshold to protect pixels from neighboring pixels. So we have to use a TFT there to isolate. So what we have here is we have a trend where we reduce complexity, cost, and power, and we do that by putting more and more of the bistable function into the optical layer. So in this situation, we're sort of heavy on electronics. Here we're heavy on physics and chemistry. Standard passive matrix addressing. How does that work? We address the display a line at a time. So we take a large strobe signal and run it down the rows one at a time, and we either add or subtract column data signals with that strobe, so that the pixel resultant is either above or below a threshold line, a threshold voltage. The rows that aren't being selected see no strobe, and they only see now the column data, which is well within the threshold. And you can run that strobe down an infinite number of lines. There's no multiplex limit to this. We can implement this with a normal SDN driver. The strobe becomes the COM, the data becomes a SEG, and we use a slightly different timing sequence compared to normal SDN addressing, but the important thing is we use the same hardware. So bistable line at a time addressing simply looks like this. We scan down through the display. The line being driven doesn't affect any of the previous lines. And at the end of that, we remove all the voltages and we maintain the image. And that image will stay there for pretty much ever for the display held between -40 and +100 degrees C. So it's a long-term bistable. It's not metastable, it's truly thermodynamically bistable. One other thing just to point out is we use a 0 to 40 volt SDN driver. What we want is plus or minus 40 volts, and we do that by sharing the voltage. So this is called voltage reduction scheme. We share the voltage between the columns and the rows, and we use asynchronous monopolar pulses here to give bipolar pixel resultants. So, what's the concept on float addressing? Here we want to take a normal TCON driver IC with common seg drivers and timing controller and add another electrical element to that, which could, for example, be a linear switch array. And this allows us to disconnect the drive circuitry from the row and column electrodes in a controlled manner during the display update. And therefore, the electronics here is not having to capacitively drive the display, and therefore, hopefully, we should get a power saving. So, if we look at various different forms here, if we have a standard, so here's a standard voltage reduction scheme for normal low impedance addressing. We've got asynchronous monopolar pulses. They can provide a select pulse here, and that hits these select voltage levels. Or you can have other combinations that provide a non-select. Non-select voltage levels are a little bit close together because the display has a voltage range over which it's partially latched, if you like. The two different ways we can apply the floating or the high impedance is we can apply it just to the COM, that's the scanning row electrode, and if you apply it to the COM, then it will appear in the resultants on the pixels. Or we can apply the float to the COM and the SEG. So a non-select data signal, we just, rather than, we apply a pulse for the select, but let it float for the non-select. And that, you can see here, has a lot more of these float waveforms in the resultant. And it was the aim of the study to say, you know, what do these float sections look like, and do they still allow us to reliably multiplex the display? Before showing some data on that, there's another concept that we can also introduce, and this is to consider using bipolar drivers. So rather than using that normal voltage reduction scheme with a monopolar driver, if we had row and column drivers that actually both supplied plus or minus 20 volts, then you're combining bipolar pulses, and that might be beneficial in what these float resultants look like. So in order to understand this further, here we consider a 2x2 portion of a bigger display, which we drive with a multi-channel arbitrary waveform generator. And in this case, at this time slot, what we've done is we're driving seg2, we're grounding com2, and then com1 and seg1 are floating. So you actually have a voltage path, which we show with this wiggly blue sort of pathway. It's a set of series capacitors. And if you look at the time slot on this scope trace, you can see here we've got the driven and grounded sections, and then at com2 and at at com1 and seg1, you see we have these little floating, or we'll call them error waveforms if you like, where the pixels just floating around. They're time dependent because as a liquid crystal reorientates, it's changing its capacitance, so that changes the balance in this system. So really, what this allows us to do is say, well, what are the form of these floating sections when we have pixels in between these two driven sections, and then now let's put those float waveforms schematically into an addressing and see how it turns out. So apologies for this; it's quite a busy graph. Quite a busy page. Let me just explain what's going on the section. On case D here, we've got the normal voltage reduction scheme addressing. In case A, we're just applying the float to an active com. So we've taken those float signals now and applied those to the row before and the row after the active row, and then look at the pixel resultants from that. We can apply the float to the com and the seg in this case, so we've got more of those float signals. And again, these are estimates because they're only derived for a 2x2 analysis of a bigger display. And then the third case was where we use a bipolar common seg driver, and now our float waveforms actually are bipolar themselves. So the key thing to look at now is these resultants. And what we see is for the select pulse, we hit the voltage levels. For the non-select, we stay within the voltage levels. But now we're preceded by this, in this floating section, by if you like, a row monopolar pulse. And this is above our dotted non-select voltage level. So that might be a problem. But right at the beginning of the talk, I said how monopolar pulses were less effective than bipolar. So what we find from this is we get a reduction in operation window, but it doesn't close the operation window completely. If we float common seg, we see two of these float monopolar waveforms, and again, they don't stop the display from updating completely. If we look at a bipolar row column driver, then we can actually end up with a very beneficial case where we now have these bipolar float signals. And what you can see is they're actually lower in magnitude than in a normal low impedance drive circuit. So this, at least in concept, gives us the possibility of having disconnecting a display in a beneficial manner during update while saving power. So we were hoping to have some data from a custom driver IC that we've had built with this architecture, but today I can only we're at the second revision of that, so I can only really show you some of our preliminary data, which we took with a display driven by a multi-channel arbitrary waveform generator. And with this display, if we drive at low impedance, we set that relative power consumption at 100%, and then we're looking at power consumption for com floating and common seg floating. And generally, when we update a display, we do two scans. We blank into a single state, which in this case is white. And already with these floating methods, we get a 40% saving with that update. Then we do a second update, and in that case, the power you use depends on the selection of black and white pixels. So if you blank white and don't do any selection, you get an incredible power saving when common seg float. and pretty good power saving when comm float. And then with checkerboard and black or wall pixels on, you get some different values here. But all of these are well within 40–50% saving, and in the best cases give you a 92% saving, a power saving on a display that's already bistable and low power. So just to sum up, we've got a technology here which has a very good threshold bistability, and that gives us some degree of robustness against drive waveform errors. So imagine those floating signals as errors, if you like, and so that removes the need to hold all the rows and columns at precise voltages during an image update. And what we've demonstrated is resulting pixel voltages still give us, in that simple matrix, we still get reliable image updating. And more importantly, and our main drive for this was, we do see significant further power savings on those already exhibited by this bistable technology. So we have a drive IC with this function being produced. We're at second revision now. It's a slightly new architecture, so it's fiddly to get it right. And hopefully I can come back at future meetings and give you some more detailed data of large matrix power savings, temperature range, that sort of thing. Thank you very much for your attention. Thank you.